Hello everybody and welcome to our webinar. Today we will discuss how to apply QuickField to electron-ion optic problems. My name is Vladimir Padnos and my colleague Alex will join me after my short introduction. For majority of practical tasks, calculation of electromagnetic fields for given configuration of electrodes and coils is the first part of any problem related to electron-ion optics, because this field affects the trajectories and should be calculated before. After the field is known, trajectories may be calculated using Newton or Einstein mechanics, and in more sophisticated cases with additional effects taken into account, like space charge distribution and accumulation, particle physics specific processes which may cause radiation, etc., etc., etc. But for the first part, determination of the fields in different configurations, QuickField is fast and convenient tool. This slide shows the set of QuickField analysis formulations available now. From this wide selection, formally speaking, only thermal and stress analysis modules are not related to the particle tracking. All other analysis options may give you a field in some particular configuration. This slide shows the set of equations which controls the behavior of a single charged particle in the non-relativistic case. Force and acceleration caused by external field in each point of the trajectory depend on the electric field stress and magnetic field flux density. Direct calculation of the non-relativistic charged particle trajectory is built in to QuickField Electrostatic Postprocessor only. However, it's rather simple to use the field calculated in other electromagnetic models and extract parameters needed for particle trajectory in magnetic or combined electrical and magnetic fields. Extraction of the field parameters may be performed for some region or even for the full finite element model, or on demand for specific point where the particle is located in given moment of time. For automatic extraction of on-demand field results, we have special technology called ActiveField. ActiveField is an object-oriented application programming interface to QuickField core functions. As you see in this slide, ActiveField functions may be called from procedures written in Visual Basic, MATLAB, C++, and a variety of other modern programming systems. This slide shows ActiveField object model. Most of functions available from QuickField user interface are available also as a programming interface. For this webinar, we have prepared a trajectory calculating script written in Excel Visual Basic, which performs numerical integration of the equations of Newtonian mechanics using the local electrostatic or magnetic fields derived from the QuickField simulation problem. You may use the script as is or modify it or write your own procedure from scratch following our example. Now my colleague Alex will demonstrate how to calculate charged particle trajectory using QuickField Electrostatic Postprocessor, and then he will show you our free open source tool for 3D trajectories in 2D electrostatic or magnetic field simulated by QuickField.
Thank you, Vladimir. Today I will show you 4 problems. 2 electric problems and 2 magnetic problems. Electric problems are the test case, the charged particle in uniform electric field in capacitor. Then the second problem is the real device, the electrostatic particle accelerator. And the magnetics problems are charged particle in uniform magnetic field in the coil and the electron length. The first problem I would like to show you is a charged particle in electrostatic field. Here we have the disk capacitor. There is the negative plate and the positive plate. And the charged particle is placed inside the capacitor. Let's make the problem from the scratch. I start QuickField and create the new problem. It's a disk capacitor. The problem type is electrostatics, and the model class is axisymmetric. Axisymmetric means that the geometry has the cylindrical symmetry. The axis of rotation is a horizontal one, and we should draw only the upper half of the capacitor. And we will simulate only the capacitor interior area. We will not simulate the external field. So this is the new problem, and I should draw my geometry model. Yes. This would be the negative plate. And this would be the positive plate. Inside is the vacuum. And I will place the charge, the point charge, inside the capacitor. Charge. It's a point charge, infinitely small, but it's also possible to specify distributed charge on the surface or volume charge. The next step is to assign physical properties to each object. For the vacuum, I specify electric permittivity. The negative plate has 0 voltage, and the positive plate has the potential of 1 volt. And for the charge, I specify the electric charge. I will simulate the electron particle, so the electric charge is the charge of the electron. Now we should build the finite element mesh. Just press one button. Save all problem files and solve the problem. You can see I got the uniform field distribution. The electric field strength in all regions is the same as 10 volts per meter. But what affect charge? How does the charge affect our field? Right now, I can see no effects from the charge placed here. Let's make the dense mesh. Usually, to get better results, you should build the dense mesh. I run the simulation again. And again, nothing. We have uniform electric field with intensity of 10 volts per meter. You can see the vectors of electric field strength. You may ask, where is the charge? Let's build the integration contour. I remember I placed the charge somewhere here. You can see there is a charge inside the contour. And there is the force acting on the charge. And the force value corresponds to the formula. Charge multiplied by the electric field strength. Electric field strength is 10 volts per meter. I multiplied by the charge value, and the force should be about 1.6 E negative 18. You can see I get the correct value with QuickField, but let's take a look closer at our charge. I will adjust the field picture. Our charge is somewhere here. Yes, this is our charge. You can see that the charge affects the field distribution in a very small area of about 1 micrometer, 1/10 of micrometer. You may ask, why it doesn't affect the field distribution in general? There are two reasons. For one, the charge is very small in size. And for second, the charge is very small in value. Let's calculate the charge stored on the capacitor plates. The capacitor plates holds the charge about 1,000,000 times higher than the electron charge. So we can remove the charged particle from the model away and simply calculate the force manually by multiplying the field strength value by the presumed charge value. Let's do it. There will be no charge now. I simulate the problem again. And to calculate force, I will measure the electric field strength The electric field strength is 10 volts per meter, and I simply can calculate the force multiplying the electric field strength by the charge of the particle. The force will be aligned with electric field stress vector in case of positive charge, or has reverse direction in case of negative charge. And this is the main principle of the particle tracer built in QuickField. The particle charge does not affect the field distribution in general. To run the particle tracer, please follow to the view particle trajectory. Here you should specify the particle parameters, the charge, the mass, and the energy. Let's place the motionless charged particle inside the capacitor. Now I should choose the emitter place. And this is the trajectory. You can see the particle trajectory aligned with the electric field strength vectors. And we put inside the negative charge, so the charge flew in reverse direction to the electric field strength. The tracer calculates the trajectories, and you can follow the trajectory and see the kinematic parameters. the velocity, the acceleration. So let's use the particle tracer and simulate the real device. Now I would like to simulate the electrostatic particle accelerator. It's a very simple device. It consists of the emitter and the ring. The emitter has negative potential and the ring has positive potential. Minus 15 kilovolts and plus 15 kilovolts. Again, the charged particle would be the electron. And the electrons are emitted from emitter and accelerated by the electric field. Our task is to calculate the final speed of the charged particle. I will create a new problem and call it accelerator. Again, it's electrostatic problem and the model class is axisymmetric. I have the drawing, so I will import the geometry model from the DXF. As the problem is the axisymmetrical, we need only the upper half of the model. And I need to build the external boundary. So what we have here, this is the emitter and I specify, I set the label to the emitter boundary. I do not need the field inside the emitter, I do not calculate the field inside the emitter. So I specify the potential on the emitter surface. And this is the ring. This is the vacuum. And the external boundary. The next step is to specify the physical properties for each material. For the vacuum, I specify the electric permittivity, for the ring, I specify positive voltage, and for the emitter, I specify negative voltage. And far away from my voltage source, the field fades to zero, so on the external boundary I specify zero potential. Now let's build the mesh, save all problem files, and solve the problem. Here is the field distribution in my electrostatic accelerator. Let's switch on the color picture. The emitter has negative potential and the ring has positive potential. Now let's put the electron at the tip of the emitter and calculate the trace. Again, I go to the view particle trajectory. The particle type is electron. I set 0 speed. This is the trace. Let's switch off the color picture. View particle trajectory. I can follow the trace and see the kinematic value. Please pay attention at the speed, at the velocity. The electron is accelerated up to 7,000 kilometers per second. And we can see that it is fly away. The beam is not focused. And about how to focus the beam, I will tell you in the end of our webinar. Next problem I would like to show you is the particle, charged particle in the magnetic field. There is the uniform magnetic field and we know the charged particle parameters and the field parameters, the flux density. We know the particle velocity, initial velocity, about it's 5,000 kilometers per second. And our task is to calculate the particle trajectory in magnetic field. As you remember, there is no need to place the particle inside the field. You can simply calculate the flux density, multiply the speed by the flux density and by the charge, and then you can find the force. Let's run QuickField and I will show you. This is the magnetostatic problem, and the model class is plane parallel. The geometry model is very simple. I have only one block, the vacuum. For the vacuum, I specify the magnetic permeability 1. And I have the boundary condition arranged so that the field will be uniform. Here you can see the field distribution. The flux density is 4 millivolts and the flux density vector directed to the left. Now if I place the particle inside the field, I can get the flux density value, and if I know the speed and the charge, I can calculate the force. And this is the main principle of the particle tracer tool. The particle charge does not affect the field distribution. The tool is written in Excel, Visual Basic for Application language. The tool is available on our website and has the open code, so you can download it and modify for your own usage. And I now will simulate the electron with the initial speed of 5,000 kilometers per second. So I specify the particle charge and the particle mass, and I specify the initial speed. There are two methods of integration implemented. I will use the deep fork integration method. The initial position, the emitter of the particle, is 0, 0, 0. It's in the middle of the area. Now let's press the button and take a look at the result. Here you can see is the particle trajectory. And I can see more details with our trajectory tool. This is the projection on the x-axis. This is the projection on the y-axis and on the z-axis. And these are the cut planes, the XY planes, the YZ plane, and the XZ plane. Also, you can see the calculated parameters, the kinematic parameters in the table sheet. You can see the time, the coordinates of the particle, the speed, the force, and the energy. As you know, the magnetic field doesn't affect the kinetic energy of the particle. So this tool is very simple in use, and let's use it to simulate the real device. This is the electron lens. You remember in previous example the electron beam was not focused, and to focus the beam the electron lens are used. The lens is simply the coil placed inside the core, and the particle flew through the lens. We know the particle parameters, the charge, the speed. So let's start QuickField and simulate the particle trajectory. The problem type is magnetostatics. The model class is axisymmetric. The problem has this cylindrical symmetry, so I will simulate only the upper half of the model. This is the geometry model. I have the vacuum, the winding, the magnetic core, and the insulation between the winding and the core. For the core, I specify the permeability, and for the vacuum, the permeability of vacuum is 1, and for the winding, I specify the current. And again, we have the external boundary with 0 magnetic potential specified on. Now, to trace the particle, we need to solve the problem. And I would like to show you how the particle would fly without magnetic field. So I set very low current in the winding. This is the magnetic field distribution. Let's take a look at the field distribution on the axis of rotation. You see there is the peak value of the flux density just inside the coil, but the field density value is very small. Let's simulate the particle trajectory in magnetic field. You remember that after our electrostatic accelerator, the particle moves astray. It's not focused. Something like this. And I would like to focus the particle. But again, initial simulation without strong magnetic field. Again, it will be the electron. I specify the charge of the electron, the mass, the initial position, and the initial speed. Let's run the simulation. You see in the weak magnetic field, the particle flew away. Let's apply some current value in the coil. I put 1 ampere in the coil. Again, I solve the problem. And place the same particle in magnetic field. It seems the current value is not enough to focus the particle, so I will place 10 ampere. Again, solve the problem. Now it's working the intended way. The particle in the strong magnetic field is focused and directed to the center. This is the focal point, and this is the focal distance. And again, I can see the plots. Yes, this is the focal point. And I can see the kinematic values in the table. Again, the energy of the particle is not changing. Magnetic field does not change the particle energy. And if I put 5 ampere in the coil, if I put 5 ampere in the coil, then I have the electronic beam that is collinear with the axis of rotation. These are the ways you can simulate the particle trajectory in electrostatic or magnetostatic field.
So we presented, Alex showed you how to use QuickField as it is with our electrostatic postprocessor, which allows you to trace the particle trajectories, or a free tool we developed to just to demonstrate how easy it is to extract field values from QuickField and make mechanical simulations, in our case in Visual Basic. But in some cases this is not enough, and you may require some specialized tool to calculate the particle trajectory, extract trajectory parameters, or design some electron-ion optic device. There are many tools on market, but usually the abilities for calculation of electromagnetic field are quite rudimentary, and more reliable solution requires calculating all the field separately and then importing the results in the particle tracking package. Two popular packages, SIMION and QuickField, may perform the charged particle trajectory analysis in the magnetic fields, and fields for these packages may be imported from QuickField. QuickField is an open source package developed by CERN scientist Rob Wenhoff, and it is a freeware tool. You may download it from CERN website, and using the instructions provided by Rob Wenhoff, import QuickField results and then perform the gaseous detector analysis with the field calculated in QuickField. Second package called SIMION, and it is developed and distributed by Scientific Instrument Services. Detailed instructions for importing the magnetic field calculated by QuickField in SIMION is published on the website, and we will now try to show you the instructional video developed by Scientific Instrument Service. Better resolution, better sound. But idea is SIMION allows import of the field from QuickField in several ways. You may use export of the field to text file, to binary file, or you may directly access QuickField through our object interface from SIMION and get field results for each point and then calculate trajectory and analyze it in SIMION package. So today we discussed different possibilities for applying QuickField for electron-ion optics problems. You may use a built-in tool for charged particle trajectory in 2D electrostatic postprocessor of QuickField. You may use our free utility as is or modify it and simulate the particle trajectory in electric or magnetic field. Or you may use a specialized third-party software which may import the field calculated in QuickField and perform further trajectory analysis. Choice is yours, and our support team will be happy to help you following any of these directions. This is all what we wanted to show you today. Please check our website for next webinars. We have extensive webinar program for this summer, and hope to see you on our next webinars. This webinar is over. Thank you.